Look at, all of our atoms can gain or lose electrons. Ionization energy looked at the ability to remove an electron to the vacuum, which meant that atom became positive. It lost a negative charge. By losing a negative charge, I will become positive. Okay? Electron affinity, which I know I was like, don't worry about it, we're just moving through it, but it was the opposite of ionization. It's taking an electron from the vacuum and putting it on the atom. What charge would the atom become? Negative. Okay? It turns out that our atoms have certain favorabilities, one way or the other, for the certain charges associated with them. Okay? They can be positive or they can be negative. Okay? What we're looking at on this image is now all of the ones the textbooks suggest that you memorize. Okay? I would argue that the textbook has way too much information on there for you to memorize, and I would erase tin and lead. Everything else on there you should memorize. Arguably, you'll have beryllium memorized as a +2 as well.
Mike,
Yes?
you had 10 on the exam, though, for this exam.
I had 10?
You had a question that had 10 in it?
I may have had tin, I'm saying the charge.
Oh, okay.
The charge you don't have to memorize.
Okay, that makes
Okay?
sense.
So we're actually layering an extra piece of information in. You had to know the name, you had to know the symbol, now you have to know the charge. Why'd you not have to know the atomic number?
Because you can find out that.
It's on the periodic table. Okay? The charge isn't blatantly on the periodic table. Okay? The next big thing that comes out of our ionic charges is this term isoelectronic. So I would argue you don't need to memorize charge. Isoelectronic means same electrons. Okay? And the question underneath, what does the atom have to look like or do to look like a noble gas? Why would I want to look like a noble gas? How many of you want to be nobility? Let's be honest. Yeah. All of us want that billions of dollars that comes with nobility, live in a castle, okay? Awesome life. We want to look like or be the nobility. What do we do to allow ourselves to appear to be the nobility?
Dress nicer.
We dress nicer. We change our clothes. We drive fancier cars, okay? So that everybody thinks we are the nobility. Guess what atoms do? The same thing. They only have that's 3 fingers, 3 components that they can change. What are the 3 components they can change? Protons, neutrons, and electrons. Okay? What happens if I change the number of neutrons?
You increase the number of electrons.
Neutrons does not change the number of anything else.
Sorry, I was thinking protons.
It changes radius.
Neutrons.
Yeah.
It changes the mass. Those 3 subatomic particles, we talked about their discoveries for a reason, okay, and the history behind them, so that you would try and remember those important facts. Neutrons only contribute to mass. Okay? By becoming heavier, do I look, well, we could make the argument, right, that we look like the nobility because all the nobles are fat, lazy people. It's a bit excessive, but, okay. Hey, I'm more noble because of that. Mass doesn't really do anything. Okay? Typically, the nobility don't look fat, right? They're excessively beautiful and all that stupid nonsense because they have the money to pay somebody to make them look that way, right? Okay? So changing the neutrons doesn't help. What else could we change? Protons. Be careful with the fingers, Mike. Protons. What happens if I change the protons?
Changes the element.
I change the element. Okay? If I want to become the nobility, I want me to exist as the nobility. I don't want to just be dead and now I'm noble. Nah, that doesn't work. Okay? So if I change the number of protons, that changes the element. I can't do that either. So the only thing left is electrons. So what I want to do is change the electrons around that atom to make it look like one of the noble gases. This is why you need to know where the noble gases are on the periodic table. It was that last column. Okay? So let's pick an element that's not a noble gas.
Magnesium.
Magnesium. Just ignore that. Magnesium has a +2 charge. Well, the whole point of this is so that it can look like the noble gases. Okay? Well, which two noble gases are closest to magnesium? Okay. I've got argon and I've got neon. Okay? How many electrons does neon have? Okay. It has 10 electrons. It has 8 valence. Okay. Whichever way you want to evaluate will work as long as you're consistent in your approach. Okay. So if you want to use valence all the way through. If you want to use total electrons, use total electrons all the way through. Okay. I'm going to stick with total electrons. How many electrons does argon have? 18. Okay. We're looking at those neutral elements. Okay. How many electrons does magnesium have? 12. So for magnesium to look like neon, what does it have to do? It would have to lose 2 electrons. Couldn't tell if it was LOSS or the other one. Magnesium to look like argon, what would it have to do? All right, everybody see that? Which is easier?
Losing 2.
Lose 2 electrons. If I lose 1 electron, what happens? Becomes what? Yes, give me more than just looking like sodium. What would its charge be? It'd be a +1. If I lose a second electron, what does it become? +2. What's the charge for magnesium? +2. Why? It's trying to look like the noble gases. The easiest noble gas for it to look like would be neon. Magnesium's a +2. We can do that same argument with every element underneath magnesium, and we'll encounter the same type of situation. Okay? Because it's in a family, we could also immediately say, well, everything in that family is going to have the same charge because they have to react the same, because that's why they're in a family. Okay? Does this really work for all of the ones up there? Yeah. Yeah, it does. Okay? So let's pick another one. Because I got a couple people saying, no, it doesn't. Okay, well, we picked a positive one. Positive things are always better because, they're positive, right? So let's be a little pessimistic. Yeah, whatever. Deaf ears, that's fine. Let's take a look at fluorine. How many electrons does fluorine have? How many electrons does fluorine have? I don't care about the charge. The charge is secondary information. 9. It wants to look like neon or helium. Those are the 2 closest elements. How many electrons does helium have?
2.
How many electrons does neon have? 10. For fluorine to look like helium, what does it have to do? It has to look like helium, answer the question asked. It would have to lose 7 electrons. Or, to look like neon, it has to gain 1. Which is easier? Gaining 1. Guess what charge fluorine becomes? Negative, because it is gaining, that sounds like a positive, but it's gaining an electron which is negatively charged.
Where's it getting it?
Good question on where it would come from. Okay? On establishing these charges, what it's coming from is another element. Okay? These electrons aren't just coming from nowhere. They have to come from some other source. Okay? So what we're looking at is for our ionic charges is when I take that element in its neutral state and I put it now near another element, what do the electrons do? In certain cases for our elements, the metals give up their electrons. Okay? They will carry a positive charge. Okay? The nonmetals will carry a negative charge because they will take electrons from the metals. Okay? So it's not just coming from nowhere, it's coming from another atom in a compound. Okay? And that could then later dissolve and do other things. Okay? But it's coming from another atom.
We don't care where.
And we don't care where. Okay? Anytime I see fluorine in a compound, it will carry a -1 charge. Okay? If I'm asked to define the charge on fluorine, -1. Answers all the way through. Okay? Anybody notice we went from positive to negative, right? Okay. What would happen right in the middle of that?
They'd be neutral. Like not have, well, they would
They
have.
wouldn't
Okay,
need
well,
it.
let's see.
I don't know, they wouldn't need it.
Let's take a look at oxygen. Let's try and find that differential. Oxygen, to look like neon, needs to do what? How many electrons does oxygen have? Man, the periodic table behind me is not fun. 8. To look like neon, what does it need to do? Gain 2. To look like helium, lose 6, which is easier. Gain 2, oxygen carries -2 charge. Nitrogen, how many electrons? I'm going to stick with the total. We can go back and do valence after class. It's okay. Nitrogen with 7. Okay. To look like neon, what does it have to do? Gain 3. To look like helium? Lose 5. Which is easier? Gaining 3, nitrogen carries -3 charge. What's that next element? Notice it's not on the list to memorize. I wonder why that is. It's carbon with how many electrons? 6. To look like neon, what does it need to do? Gain 4. To look like helium? Lose 4. Which is easier? It can go either direction, which means we don't memorize the charge because depending on what it's bonded to, its charge will change. Okay? So the ones you're asked to memorize are the ones that are always that charge. They don't change charge. Okay? In, unfortunately, ionic systems. Okay? And we have to be careful on that. We have to be looking at an ionic system. Okay? Kind of makes sense? So I made an emphasis there. What is an ionic system, or is that what you're going to ask me?
No.
Okay, go with your question.
So do noble gases have a charge of 0?
Noble gases will have a 0 charge, always. So what is an ionic system? A system with charges in it. How do I know I have charges? Is this system ionic, H2O? No. So I won't look at charges when I look at H2O. Okay. How about CH3, CH2, OH?
They're not just sharing electrons, they're taking away they're taking away and adding electrons to it.
Ooh, now we're getting an interesting idea. We're talking about the ability to share those electrons. And in an ionic system, we don't share electrons. Okay, we have a complete transfer of electrons from one atom to the other. If it's not ionic, what is it? Covalent. How do you know you have a covalent system? Crap, we're trying to figure out the ionic system, but now I'm throwing another system at you, saying covalent.
The electrons are being shared instead of taking.
How do we know the electrons are being shared in a covalent system?
A little line in between it.
Whoa. What kind of system am I looking at here in red?
Table salt. Sorry.
No, you're right, it's table salt.
I'm surprised you wrote that.
That one's ionic. Why is that one ionic? This goes back to the definitions of the bonds, which was in the Lewis structure video, which was in chapter 12. Your ionic bonds are, by definition, metals and nonmetals. Is carbon a metal? No. Is hydrogen a metal? No. Is oxygen a metal? No. Is CH3, CH2, OH an ionic system? No. There is no metal there, not an ionic system. Okay? We need to be able to establish those. How do we decide our ionic versus covalent? Well, we came up with it. Ionic, our quick rule of thumb, it has to have a metal. Okay? It's ideally a metal and a nonmetal. If we got those two, it's ionic. If we don't have a metal and a nonmetal, well then it's not ionic, we don't worry about the charges. And that's all we needed for that. Make sense? Okay.
Can you have a metal and a metal?
Sorry, I'll come back to you. I don't remember answering your question. What was your question?
The charge on a noble gas.
Oh, I did answer that, right? Okay.
Can you, I'm not sure if I understand if you can bond a metal and a metal together.
Can you bond a metal to a metal? Yes. If it is the same metal, it would be an element. What if it's a different metal? It's an alloy, right? What kind of bond is associated there? It's a metallic bond. We're not worried about that for this class. Okay? Where this would eventually go into is now applying this out using our Lewis structures and look at a compound. Okay? Theory, some of us had this compound this morning. Caffeine, which is found in our coffee. Okay? If we had to go through and evaluate this, that might be a bit difficult to have to draw that every single time. Depending on what we're trying to do, we may not want to draw it all. We may want to condense that down. What can we condense it down into? As a subtle hint, you know me on subtlety, I want a formula. So I can go through and say, how many carbons are there? Oh, can I count that high? 1, 2, 3, 4, 5, 6, 7. I get 8. Hydrogen, I really don't want to count that high. 3, 6. Oh, that wasn't that bad. 10.
Like 9.
I think I got 10. Oxygen. 1, 2. Nitrogen. You got 4? I got 4. And we could look at the chemical formula. Those numbers, as subscript, are referring to what's directly in front of them. There are 4 nitrogens. There are 2 oxygens. There's 10 hydrogens. 8 carbons, right? Okay. So when we look in general chemistry, we tend to go simplify all the way down to the chemical formula, because what we're concerned about is not necessarily how that molecule reacts by looking at the pieces of it, just that it reacts, and these are the quantities that it reacts in. Okay? Which is a bit unfortunate, because that then brings in a bunch of mathematics, and that tends to lose everybody. Okay? But that's what we do in 130. So when we're looking at a chemical formula, okay, we're trying to just simplify it down. Are there other things that we could do within that formula? Okay? Let's take a look at, whoops, wrong, still the wrong pen. That lower left. Does that lower left one follow the pattern that we just discussed? No. No. If we follow the pattern, it should have been C2H4O2, right? Why did we show the hydrogen out front?
Because it's got a...
Because hydrogen has to bond with...
That hydrogen has something special and different than the other hydrogens. Okay? What I'm trying to call attention to is that that compound is acidic. Okay? Or known in other circles as an acid. We haven't learned about acids yet, but you will by next Monday's class, because you're going to watch the nomenclature video. Okay? Or read the nomenclature chapter. Okay? So we will change our formulas sometimes to highlight certain functionalities so that we can look at a formula and very quickly call attention to what's going on with it. Same kind of thing is happening over here with this compound. I'm separating that hydrogen away so that I can call attention to that functional group. Okay? If I embed the hydrogen in the formula, I lose that information. Okay? We go back and forth within this class on showing that information and not. Okay? The default is not showing that information, just so you're aware. Kind of make sense?
Right, each side.
Yeah. Okay. We could also go through and look at a chemical equation, right? H2 plus O2, reaction arrow H2O. Okay. We're looking at how those things get combined and put together. This is a recipe. I take hydrogen, I take oxygen, and it makes H2O. Okay. I can do the same thing for making sandwiches. I take bread, I take cheese, and I make a sandwich. Okay. Is there some information missing from my prep for making a sandwich? Yeah, what do you mean? Okay. How about the amount of bread? The amount of cheese? Same thing's missing from this. We aren't quite there yet, but we're darn close. Okay? Chapter 12 gave us the types of bonds. This was the section that I said we needed to go back and review. We've got our ionic bonds and our covalent bonds. Ionic bonds are metals and nonmetals. Covalent bonds are two nonmetals. Okay? Let's take a look. Are all nonmetal covalent bonds the same? H2O, HCl. Can anybody name H2O for me? Water. Can anybody name HCl? Hydrochloric acid. Okay? Same type of bond, right? They're both covalent bonds. Okay, well, if they have the same type of bond, they should have the same kind of reactivity, right? So I can douse myself in water and douse myself in hydrochloric acid and get the exact same response. No. Okay? Don't douse yourself in hydrochloric acid. Really bad idea. That's like melting your skin. Bad, bad, bad. Okay? So what does that mean about the bond? There has to be another type of bond. What was that other type of bond? Our polar covalent bonds. Okay, where we're starting to transition between purely covalent and purely ionic. Okay? When we look at our ionic bonds, it breaks down into two components. Okay? Our metal will typically be the cation, the positive charge. Why would our metals typically be a cation?
Because it's losing.
Our metals, think group 1 and group 2, are all trying to lose electrons to look like the nonmetals. Okay? It's easier for them to lose electrons. Okay? So your metals will always carry the positive charge. Okay? Your anion, or the negatively charged species, will be your nonmetals. Why will the nonmetals be negatively charged? It's easier for them to gain electrons to look like our noble gases than it is to lose. Make sense? Okay? Because all of these charges are now inherently unstable, when we look at a compound of, say, sodium chloride, there's lots of sodiums alternating with chlorides in a very regular pattern. Okay? So I can't go through and say this is a molecule of sodium chloride, because to do that, I'm breaking a whole bunch of other bonds with the rest of the structure. Okay? For this reason, when we reference ionic compounds, we don't call them molecules. Okay? And by we, I mean the textbook and whoever writes our final exam. Instead, we refer to our ionic compounds as formula units. We take the smallest whole number ratio of the metal and the nonmetal, and that's what we call our formula. So if we went through and looked at the structure shown up there, if we had sodium and chloride, we have tons of sodiums and tons of chlorides within that. Okay? We know it balances out. Nobody check my math, please. Don't. Okay? I see 7 sodiums and 7 chlorides within that structure. So my formula is Na7Cl7. What if I look at a larger sample of sodium chloride? Okay? Na70Cl70. Okay? Is that a new compound? No, it's the exact same stuff. That's why when we look at our ionic compounds, we take it all the way down to the reduced ratio, and we'd reference it as just NaCl, where we have implied 1 and 1. Make sense? Okay. NaCl is now the formula unit for sodium chloride. It's the smallest molecule, if you will, for that compound. And our ionic bonds. When we go through to make the ionic bond, what's happening between sodium and chloride? And this gets to Paul's question, where did these electrons come from or go? Well, when I take a sodium atom and put it near a chloride atom, what happens? The sodium says, I don't want this electron. I'm going to give it away to another atom. How would I know sodium is inclined to do that? We could use metal. There's a better word that I would like you to use to associate with, but metal will technically get you there. Not charge either. That's still back to the metal definition. It's a big one. We could play hangman, except I don't know how many letters to draw out. That's how blanks it is. Electronegativity. The ability for one atom to steal electrons from another. Sodium has a very low electronegativity, meaning it does not want to steal electrons. Chloride, on the other hand, has a high one, meaning when I bring sodium near chloride, sodium says, I don't really want the electron, and chloride says, I do. And chloride will take that electron away. This means that we would end up with sodium as a positive charge and the chloride as a negative charge. What happens to the size of those atoms now? Everybody's favorite question, looking at sizes.
They change.
So if they're sharing it, you're adding both radiuses if it's...
Okay. So good. What we're looking at is bringing those two atoms together and looking at how the electrons are shared between them. But in an ionic bond, they're not shared. It's a transfer of electrons. So the internuclear distance, okay, will be the same as the radii, the sum of the radii. But what I'm asking about is what happens to the sodium atom's radius? Does it change?
No.
Okay. Sodium atom has how many electrons? 11. Sodium ion, or cation, has 10. So I heard a bunch of people saying, well, the radius does not change. Right? When we change the number of electrons, do we see a change in the radius? Very typically we do. Okay? Think about down a column. Okay? When we moved left to right, we didn't, because we made the nucleus stronger. Okay? And that's why it got smaller, right? So what's happening? I got rid of an electron, but what did I do to the nucleus? Nothing. So the nucleus is holding with the exact same force, but now it's holding less stuff. What does that do to the radius?
Reduces it.
It shrinks it. The radius of the sodium atom becomes ever so slightly smaller, or sodium ion. What happens to the chloride?
Becomes bigger.
It's going to become bigger. I've added an electron, and I've added it to the exact same energy level, but what else did I not change? The nucleus. So the nucleus is the same strength, and I've put more stuff in for it to hold. It can't hold on to it as tightly, and what's going to happen? It'll swell.
Is that delta predictable?
I'm sure it is mathematically. Do I know that formula? No. To calculate that exact difference. But whenever we bring an ionic compound, whenever we make an ionic compound, your metal radius will always shrink. The non-metal will always grow. That is predictable. How much it grows and shrinks, I'm sure someone's done it, but it's outside the scope of what we're doing. Whenever we make an ionic compound, the metal radius will shrink. The non-metal radius will grow. Okay? If we look at the internuclear distance between those atoms, so internuclear, meaning I'm looking at the nucleus of one and the nucleus of the other, and I want to know that distance. Whoa, that was not the button I thought it was. It ends up coming out darn close to the sum of the radii. Right? And this picture is not the greatest, but
Because the delta for the increase is the same as the delta for the decrease, so the distance really isn't going to change. Is that what you're saying?
nope, I'm not even looking at the reactant side. I'm just looking at the product side in this case. The ionic compounds. So that difference could be true. If someone wants to do the math, you could check that. It looks like it does shape out. But if we take the radius of the sodium ion and the radius of the chloride ion, that distance between those two is now the sum of those radii. I'm not evaluating the radii of those.
Okay.
Okay. Covalent bonds. Okay. We're now sharing electrons. Okay. I think I called ionic bonds somewhere, like the 2-year-olds, because they just steal stuff, so I've been told. Okay. If we move to covalent bonds, they're now sharing electrons. Okay. Not necessarily equally. Okay. That amount of sharing is going to come back to the difference in electronegativity. If they have the same electronegativity, then by definition, they will share electrons equally, because they're the same. If they're unequal, they won't share quite the same. So what happens when we go through and form a bond, say between hydrogen and chloride? Because they are now sharing electrons, we do not look at radii, okay, or ionic radii. Why do we not look at the ionic radii?
Because the nucleuses are closer.
So yes, the nucleuses are closer, but that's not why we're ignoring the ionic radii. The ionic radii.
Because there's no,
The ionic.
because there's no metal.
There's not a metal. There's no reason to look at the ionic radii because there's not an ion. Okay? That's why I won't look at the ionic radii. Instead, what I'll be doing is looking at the radius of each of the individual atoms. Because it's a covalent bond, the electrons must be shared between them, which means we've now shrunk the distance between the atoms. Because their orbitals have to overlap to share those electrons. Make sense? Okay. What about this not necessarily equally, partially? So let's take a look at HCl as it's drawn there. Okay, we have hydrogen bonded to chloride. Okay, if I want to predict something about the reactivity of that molecule, what I will do is look at electronegativity and look at the difference between those. And what I will find is hydrogen's electronegativity is very, very low, and chloride's is very, very high. What does that mean about the electrons in that bond? Where will they spend most of the time? Towards the chloride. If those electrons spend most of their time with the chloride starts to become what charge? Negative. It's stealing those electrons from the hydrogen. Well, if the chloride became negative, what happened to the hydrogen? It would have to become positive. That looks an awful lot like a cation and an anion. And when do I see a cation and an anion? When I have a ionic bond. Do I have an ionic bond? No, so I cannot use this notation. I still want to draw attention to these charges that are building, but they aren't formally there. So I have to invent a new notation. That notation still wants to maintain the negative charge and the positive charge, but what I'm saying is I'm not all the way negative, I'm not all the way positive. I'm part way there. There's a small differential that's becoming that charge. How many people have done calculus? Okay. When we're looking at calculus and we do derivatives, what's the symbol usually dropped in there?
It's an upside down.
It's usually a capital delta for a derivative. For this, we're going to be using the same kind of process. The reason we don't use delta is a capital delta is it's used for another symbol. We use a lowercase delta, which as Paul is referencing, this really weird curly thing. That is my attempt at drawing a delta. Okay? It is a lowercase delta symbol, saying a partial charge is building. That is the partial charge notation that I believe might have been in the practice exam that I probably should have crossed out. I apologize for that. Okay? But that's where it is. Make sense? Okay. Bond energy. Okay. When I make a bond, what do we expect to happen to the energy? Should the energy go up or should the energy go down? Okay, so we got same. I heard up. Anybody want to say down?
Sure.
We got it down. We got all three. When you came in here, what did you do?
Well, sat down.
You sat down. Why'd you sit down?
Because I was expending energy coming in here.
Okay. Took energy to come in. Fair enough. Okay. Why are you not standing? That would take more energy.
We don't have enough.
So when you come in, you are going to your lowest energy state. Okay. If we could, you would probably all lie down. That would look a little weird. Okay. But you could do that. Some people already do that. They come in and be like, yo, peace, I'm here, I'm going to go sleep. That's cool. Okay, that's your call. Okay, we're going to our lowest energy state. What do we know about bonds? Do they happen?
Yes.
Yes.
Yes. That's why we exist. Yay, bonds. If bonds were higher in energy than the atoms, would I ever make a bond?
No.
No. What does that mean about the energy of the bond? It is lower in energy than the atoms. Where did the energy go? difference in energy there.
To sleep.
They lay down.
What we're starting about is we have atoms at relatively high energy, and we have bonds at lower energy. To go from atoms to bonds, don't worry as much about the
They use
line in
energy
between.
to make bonds?
We need to,
There's an energy difference there. That's energy that is now released to the system as
heat.
They make
heat.
bonds?
This is one of the reasons why when we look at physics and continual motion, infinite motion, what's that stupid? Perpetual, thank you. Perpetual motion machines don't work largely because of heat. Okay? It is released into the environment and we can't capture that back to the same level of efficiency. So when we make a reaction, when we go from atoms to bonds, what happens? We release energy. How do I add that into my diagram?
Fire?
Release of
Okay.
energy.
I could draw a fire. Where would I draw the fire? Okay. I've got fire all the way around everything. That sure looks like I've got fire as a reactant now. That means energy is a reactant. No, it said we released heat, right?
In the bond.
Where does that energy need to be shown? Yes, energy was in the bond, but there's that extra energy that we haven't accounted for yet.
Just outside of it.
Let's draw the fire over here. That's my attempt at a fire. There's a blue flame.
Is there a burning bush?
Okay. How many people are good at drawing fires? Okay, so let's come up with a different way to represent our energy.
Oh, draw the bacon. Or
The bacon?
You know, like when you put your hands under the thing, it shows bacon instead of hot air.
What are you talking about?
The steamy bacon.
That's still drawing. I'm not drawing. What might be a useful symbol for energy?
E.
There we go. E for energy. Or F for energy. Okay? We now have energy released from our system when we do this. Okay? When we're looking at bond energy, by definition, it is the atoms in their neutral state in the gaseous form. When those two atoms in their gaseous form come together to form a bond, we're now releasing energy. Okay? So when we're talking about bond energy, that's what we're referencing. Is that what we typically look at when we look at bonds making and breaking? No. We're probably in solution. We're probably in our bodies. We're not looking at gaseous form happenings. Okay? That energy becomes vastly more complicated because we're adding a lot of other stuff into it, and you can see the energy show up on both sides of the equation in those circumstances. For the sake of this class, we're only concerned about this whole gaseous state system. Okay? When we run a reaction with those elements in their gas form to make a bond, we will release heat. What if I take HCl in that gaseous form and I now break the atom apart from each other? So now what I'm saying is my reactant is HCl. I will then make hydrogen and chlorine. Where should the heat show up now?
Inside the atom.
Heat, we've tried the whole putting it in the structure already. The heat is an external force to our structure, so we can't just put the heat and say it's in there. It's not in there. It goes on the left-hand side of the equation. Because that heat, to cause this to happen, to break those apart, I'm putting in energy to force those apart. Okay? That could be it just existing on its own. Okay? It could be that heat is me physically breaking them apart and providing that energy. Okay? So when we look at this, this is kind of neat. I can change the direction of the reaction, okay? But by doing so, I have to include everything that was a reactant and make it a product. Everything that was a product and make it a reactant.
So you flip the equation.
Okay? All we're doing is flipping the equation. Okay? Ah. Sorry, that was an exaggeration. I don't care. So, that gets us through the old stuff, officially what we should be looking at in the next 3 minutes. Woohoo! The unfortunate chapter of our PSS, if you're using chapter 7, or if you're edition 7, or chapter 2, or parts of chapter 2 if you're using edition 6 in our textbook. The biggest part of this is significant digits. Because you've done some of this in lab, I'm kind of running under the assumption you're somewhat comfortable with it.
Just for VR.
Okay? at least somewhat. So I would presume that we can move through this relatively fast. Okay? So we'll go ahead and start it off. The biggest deal here is our significant digits. Okay? So we have measurements. Measurements, number, and unit. Do not just give me a number. Do not just give me a unit. Okay? The unit is in red and big bold letters. Why is the unit in red, big bold letters, but the number not so much?
Because the number's meaningless without the unit.
The number is completely and utterly meaningless without the unit. When we go through to solve questions, what I will ask you to provide is the unit. The number is tied to the unit. If you know the unit, you can solve any question. If you know the number, you're SOL. Okay? When we look at distance or length, we got meters, all sorts of other fun units. Okay? The standard that we use is the metric system. Okay? Thankfully, because the US isn't in the metric system, we now have to be able to convert between them. Yay for you. Okay? So if we continue on, mass measurements, we use a balance. There's a neat little video there. If you want to watch that, feel free to go ahead and do so. We're not going to watch it now. Okay? Mass and weight officially are not interchangeable, though I will probably interchange them throughout the semester. Okay? And you will see your textbook interchange them as well. Okay? Volume measurements, graduated cylinders, syringes, burettes. Volume measurements are used for liquids because they aren't as easy to pour onto a balance because they hit the balance, they will roll off. Okay? If you spilled them on a balance, it ruins the balance. Okay? So we tend to use graduated cylinders and such. Measurements and uncertainty. What is the length of that rod?
Length of
That silver little bar there. What is the length of that? 4.3, 4.2
something.
centimeters. 4-ish centimeters. Okay? Thank you everybody for participating. 4-ish is wrong. And not just because we said ish. Okay? When we observe a measurement, we take all of the exact values and we guess one more place. What if I'd written 4.25 centimeters? That is wrong. I've guessed an extra decimal place. The 0.2 is a guess. Guess what the 5 is?
Super guess.
A super guess. No super guessing. Okay? So we can't use 4.25. That is also wrong. Okay? If we want more information, what we would have to do is add in more tick marks. Now we could increase the number of sig figs, right? Okay. Uncertainty, let's ignore that. Sig figs. So this is a good one to end on. How many sig figs? Let's get a shout out as we move through. First number.
2.
1. Next number. 2. Next number. 3. Next number. 2. Next number. 1. We need to review sig figs. Okay. In that review, I promise this is where I'm going to end. Come on, move, slide, move. Move. Come on. 3 rules. No more, no less. 3 rules covers all sig figs. I think your textbook lists 5 or 6. Every other instructor I've seen lists 5 or 6. There are 3 rules. Every single question can be answered with those 3 rules when it comes to sig figs. Okay? And with that, we'll go ahead and stop. We will do all of those on